Today we are going to talk about how to perform a harmonic regression time series analysis on imagery from Landsat using the geodesic platform. Geodesic is an analysis and decentralized data platform optimized for spatio-temporal data. We will be using a part of the platform for large-scale compute called Tesseract. Harmonic regression is a common time series analysis technique used in forestry and agriculture. It is useful for finding patterns in data where the patterns repeat with a known period, which in the case of vegetation is usually yearly. Harmonic regression can be used to understand trends in the data as well as predict values for future seasons. Datasets in geodesic are kept in a knowledge graph that can allow datasets to be linked to entities, models, and other datasets so that you know not only what datasets are available, but what they are good for and how they can be used. For this demo, we will use data from the Landsat 8 archive in Google Earth Engine. Using the geodesic platform, external datasets are easy to add without the need for copying large amounts of data. Here we can see adding a dataset from Google Earth Engine is simple and only requires a few pieces of information: the name you would like to give the dataset, the asset in Earth Engine, and any credentials needed to access it. Landsat is now in our knowledge graph and can be used in any other part of the platform. To use Tesseract, we must first create a job that will describe what we want the system to do. Here we give the job a name, the spatial bounds it should perform the processing over, as well as what spatial reference we would like the output to be in. Next, we create an input asset. This tells the job what data to gather to be used in subsequent steps of the job. We will use the Landsat dataset we just created as our input. For this job, we want to use the first 6 spectral bands available in Landsat. Data gathering and collation is especially difficult with spatio-temporal data. In many analysis platforms, time is a tacked-on feature that gives you little more than a slider bar. Tesseract was designed to treat time as a first-class citizen from the very beginning. As you can see here, we can specify how we would like Tesseract to temporally bin the data for us. In this case, we are asking for strided time bins that are 8 days wide with an 8-day stride and 200 total time bins, which correspond to approximately 5 years of Landsat data. For this job, our binning will look like this. Any data that falls in one of these 8-day bins will automatically be mosaicked and gathered for us. As another example, if we had asked for 1-day bins with a 3-day stride, our binning would look like this. Any data that falls outside of the selected bins will not be included in the input data. Proper time binning is typically one of the most difficult parts of preparing spatial data for analysis. Tesseract provides a powerful, flexible interface for time binning that reduces the problem down to specifying just a few numbers. Now we can add the modeling step to the job. Models in Tesseract are Docker images that can easily be built using the Tesseract Python SDK, which we will look at in a moment. After specifying which image to use, we need to tell Tesseract what to use as the input step and what outputs to expect from the model. Our model step will use the Landsat output from our previous step. Finally, we can submit the job and watch its progress using the monitoring widget. Tesseract will spin up the requested number of workers to complete all steps and spin them down when finished to minimize compute costs. Let's take a quick look at what the model is doing. Writing a model to run in Tesseract is easy using the Python SDK. All we need to do is define 2 functions, inference and getModelInfo. Inference tells Tesseract what processing to run on each chunk of data. No need to worry about tiling or recombining data. Tesseract will handle that for us. The getModelInfo is used for validation and tells Tesseract what inputs and outputs it should expect. In this case, we are running a least squares regression, treating every pixel as its own time series with 5 years of Landsat data. In this demo, the model performs over 2.2 million regressions total for all pixels in the defined area. Once we have wrapped this code in a Docker image, it is ready to be run in Tesseract. Array outputs from Tesseract are stored in ZAR format on cloud storage and can be easily retrieved from the job. Let's grab the assets from our job and check the output. Here we create an RGB image using the 4th regression coefficient from the 3 output assets.